prepare for the Washington State Electrical exam, focus on the Washington State Electrical Code, specifically Articles 100, 210, 220, 300, 400, and 514. You should also consult the National Electrical Code 2020 Reference Manual as a supplementary resource for additional details and explanations on National Electrical Code rules. Review Washington State Washington Administrative Code 296.46. B. Focusing on electrical administrative rules specific to Washington State. Practice load calculations using methods such as Associated General Contractors, Institute of Electrical and Electronics Engineers, and International Energy Conservation Code methods. The exam is likely to include a load calculation question. The specific load calculation method may vary, but some common types include branch circuit load calculations, feeder and service load calculations, transformer load calculations, motor load calculations, and lighting load calculations. For branch circuit load calculations, you need to determine the ampacity and overcurrent protection requirements for branch circuits. For feeder and service load calculations, you need to calculate the total load on a feeder or service and determine its size and protection. Transformer load calculations involve determining the kilovolt amps rating and protection requirements for transformers. Motor load calculations involve calculating the horsepower, current, and voltage requirements for motors. Lighting load calculations involve determining the wattage and circuit requirements for lighting fixtures. Other topics covered include code interpretation and application, electrical safety and code enforcement, electrical equipment installation and maintenance, wiring methods and materials, grounding and bonding requirements, and electrical plans and specifications. Firstly, let's discuss branch circuit load calculations. The National Electrical Code provides guidelines for calculating branch circuit loads to ensure safety and prevent overloading. A branch circuit is a circuit conductor between the final overcurrent device protecting the circuit and the outlet or device. To calculate the load on a branch circuit, you need to consider several factors including the type of occupancy, the connected load, and any applicable demand factors. For general lighting loads and dwelling units, the National Electrical Code Table 220.12 specifies a minimum lighting load of 3 volt amps per square foot. This value is used to calculate the total lighting load for the dwelling. For other occupancies such as commercial or industrial buildings, the lighting load requirements may vary depending on the specific use of the space. In addition to general lighting loads, you also need to consider the load imposed by receptacle outlets. National Electrical Code Section 220.14 I specifies that each receptacle outlet in a dwelling unit must be calculated at not less than 180 volt amps. This value is used to determine the total receptacle load for the dwelling. For non-dwelling occupancies, the receptacle load requirements may vary depending on the specific use of the space. Once you have determined the total lighting and receptacle loads for the branch circuit, you can calculate the total load by adding these values together. The resulting value represents the total load that the branch circuit must be capable of carrying. It is important to ensure that the branch circuit is properly sized to handle the total load. The National Electrical Code specifies the allowable ampacities of conductors in Table 310.16. The ampacity of the conductor must be equal to or greater than the total load in the branch circuit. In addition to the conductor size, you also need to select the appropriate overcurrent protection device for the branch circuit. The overcurrent protection device is designed to protect the circuit from overloads and short circuits. National Electrical Code Section 240.4 specifies the requirements for overcurrent protection. The overcurrent protection device must have an ampacity rating that is equal to or less than the ampacity of the conductor. Secondly, let's consider feeder and service load calculations. A feeder is a circuit conductor between the service equipment and the final branch circuit overcurrent device. A service is the conductors and equipment that deliver electrical power from the serving utility to the wiring system of the premises served. To calculate the load on a feeder or service, you need to consider all of the loads that will be connected to the feeder or service. This includes lighting loads, receptacle loads, appliance loads, motor loads, and any other loads that will be drawing power. The National Electrical Code provides guidelines for calculating feeder and service loads in Article 220. The first step in calculating the feeder or service load is to determine the general lighting load. As mentioned earlier, National Electrical Code Table 220.12 specifies a minimum lighting load of 3 volt amps per square foot for dwelling units. This value is used to calculate the total lighting load for the dwelling. For other occupancies, the lighting load requirements may vary depending on the specific use of the space. Next, you need to consider the receptacle loads. National Electrical Code Section 220.14 specifies that each receptacle outlet in a dwelling unit must be calculated at not less than 180 volt amps. This value is used to determine the total receptacle load for the dwelling. For non-dwelling occupancies, the receptacle load requirements may vary depending on the specific use of the space. In addition to lighting and receptacle loads, you also need to consider the load imposed by appliances. The National Electrical Code requires that appliances be calculated at their nameplate rating. This means that you need to use the voltage and amperage values listed in the appliance to calculate the total load. For example, if an appliance is rated at 120 volts and 10 amps, the load would be 1200 volt amps. Motor loads are another important consideration when calculating feeder and service loads. The National Electrical Code provides specific rules for calculating motor loads in Article 430. The general rule is that the motor load must be calculated at 125% of the motor's full load current rating. This is to account for the fact that motors can draw more current when they're starting up. Once you have determined all of the individual loads, you can calculate the total load on the feeder or service by adding them together. However, the National Electrical Code allows for demand factors to be applied to certain loads. A demand factor is a multiplier that is applied to the load to account for the fact that not all of the loads will be operating at the same time. For example, National Electrical Code Table 220.42 allows a demand factor of 70% to be applied to the general lighting load in a dwelling unit. This means that only 70% of the total lighting load needs to be included in a feeder or service calculation. After applying any applicable demand factors, you can calculate the final feeder or service load. This value represents the total load that the feeder or service must be capable of carrying. It is important to ensure that the feeder or service is properly sized to handle the total load. The National Electrical Code specifies the allowable ampacities of conductors in Table 310.16. The ampacity of the conductor must be equal to or greater than the total load on the feeder or service. In addition to the conductor size, you also need to select the appropriate overcurrent protection device for the feeder or service. The overcurrent protection device is designed to protect the circuit from overloads and short circuits. National Electrical Code Section 240.4 specifies the requirements for overcurrent protection. The overcurrent protection device must have an ampacity rating that is equal to or less than the ampacity of the conductor. Thirdly, consider transformer load calculations. Transformers are used to step up or step down voltage levels in electrical systems. They are rated in kilovolt amps, which represents the apparent power that the transformer can deliver. To calculate the kilovolt amps rating of a transformer, you need to know the voltage and current on both the primary and secondary sides of the transformer. The formula for calculating kilovolt amps is kilovolt amps equals voltage times current divided by 1000. For example, if a transformer has a primary voltage of 480 volts and a primary current of 100 amps, the kilovolt amps rating would be 48 kilovolt amps. The same calculation can be performed on the secondary side of the transformer to verify the kilovolt amps rating. It is important to select a transformer that is appropriately sized for the load that it will be serving. The transformer must be able to handle the maximum demand load without overheating or experiencing excessive voltage drop. The National Electrical Code provides guidelines for sizing transformers in Article 450. In general, the transformer kilovolt amps rating should be equal to or greater than the calculated load. However, there are some exceptions to this rule. For example, if the transformer is serving a motor load, the kilovolt-amps rating may need to be increased to account for the motor's starting current. In addition to the kilovolt-amps rating, you also need to consider the overcurrent protection requirements for the transformer. The National Electrical Code specifies the requirements for transformer overcurrent protection in section 450.3. The primary side of the transformer must be protected by an overcurrent device that is sized no greater than 125% of the transformer's primary current rating. The secondary side of the transformer must be protected by an overcurrent device that is sized no greater than 125% of the transformer's secondary current rating. These overcurrent devices are designed to protect the transformer from overloads and short circuits. Fourthly, motor load calculations. Motors are commonly used in electrical systems to power various types of equipment. The National Electrical Code provides specific rules for calculating motor loads in Article 430. The first step in calculating a motor load is to determine the motor's full load current rating. This information can be found on the motor's nameplate. The full load current rating is the amount of current that the motor will draw when it is operating at its rated horsepower and voltage. Once you have determined the motor's full load current rating, you can calculate the motor load. The general rule is that the motor load must be calculated at 125% of the motor's full load current rating. This is to account for the fact that motors can draw more current when they are starting up. For example, if a motor has a full load current rating of 10 amps, the motor load would be 12.5 amps. In addition to the motor load, you also need to consider the overcurrent protection requirements for the motor. The National Electrical Code specifies the requirements for motor overcurrent protection in section 430.52. The overcurrent protection device must be sized to protect the motor from overloads and short circuits. The maximum allowable size of the overcurrent protection device depends on the type of motor and the type of overcurrent protection device. For example, if the motor is a single-phase motor and the overcurrent protection device is a circuit breaker, the maximum allowable size of the circuit breaker is 250% of the motor's full load current rating. If the motor is a three-phase motor and the overcurrent protection device is a fuse, the maximum allowable size of the fuse is 175% of the motor's full load current rating. It is important to select the appropriate overcurrent protection device to protect the motor from damage. Fifthly, lighting load calculations. Lighting is an essential part of any electrical system. The National Electrical Code provides guidelines for calculating lighting loads in Article 220. The first step in calculating a lighting load is to determine the type of occupancy. The type of occupancy will determine the minimum lighting load requirements. For example, National Electrical Code Table 220.12 specifies a minimum lighting load of 3 volt-amps per square foot for dwelling units. This value is used to calculate the total lighting load for the dwelling. For other occupancies such as commercial or industrial buildings, the lighting load requirements may vary depending on the specific use of the space. Once you have determined the type of occupancy, you can calculate the total lighting load. To do this, you need to multiply the square footage of the area by the minimum lighting load requirement. For example, if a dwelling unit has the square footage at 1,000 square feet, the total lighting load would be 3,000 volt-amps. In addition to the general lighting load, you also need to consider the load imposed by any special lighting fixtures. For example, if the dwelling unit has recessed lighting fixtures, you need to calculate the load imposed by these fixtures. The load imposed by recessed lighting fixtures is typically calculated based on the wattage of the lamps used in the fixtures. The National Electrical Code also provides rules for calculating the load imposed by electric vehicle supply equipment and photovoltaic systems. Other important aspects include code interpretation and application. A thorough understanding of the Washington State Electrical Code and the National Electrical Code is essential for safe and compliant electrical installations. Code interpretation involves understanding the intent and meaning of the code requirements. Code application involves applying the code requirements to specific situations. Electrical safety and code enforcement are also important considerations. Electrical safety involves protecting people and property from electrical hazards. Code enforcement involves ensuring that electrical installations comply with the code requirements. Electrical equipment installation and maintenance are also important topics. Electrical equipment must be installed and maintained in accordance with the manufacturer's instructions and the code requirements. Wiring methods and materials must comply with the requirements of Chapter 3 of the National Electrical Code. Grounding and bonding requirements are essential for electrical safety. Grounding and bonding help to protect people and property from electrical shock and fire hazards. Finally, electrical plans and specifications are essential for complex electrical projects. Electrical plans provide a detailed representation of the electrical system. Specifications provide detailed information about the materials and equipment to be used.